Hello, everybody. It's a bit loud there. I'm glad everybody could show up for the last talk of the day. I'm going to try to get a little bit of energy here to keep everybody awake, because I know there's a lot of talk, a lot of information, but hopefully I can tell a compelling story today so you guys can learn a little something. The talk is called Distributed Scheduler Hell. But really, it's a story of how we moved a couple hundred virtual machines onto containers, because that's a really cool thing to do. And we experienced a lot of pain and heartbreak along the way, and I wanted to share our story. I always think that it's more interesting to give talks about what went wrong than went right, because that way you don't make a lot of the same mistakes that we made along the way. So hopefully I can give you a bunch of grief that you can just totally avoid. Before I start, I'm really curious, because I know my title is a bit strange. How many people here actually know what a distributed scheduler is? Like only about 5 people raise their hands. Okay, so that's actually kind of cool. So then I can really kind of dig into this. So you are more than likely already using a distributor scheduler today and you don't know it. So your cloud hoster like DigitalOcean, Amazon, Google are a distributed scheduler. They're taking virtual machines and they're putting them onto different physical machines behind your back, and you don't even really realize this happens. And a lot of people don't realize that really fundamentally cloud hosting is distributed scheduling. Because you just think, oh, I get a virtual machine and that's it. But that virtual machine has to come from somewhere, right? What I think a lot of developers think of when they think of distributed schedulers is they think of things like Kubernetes. They think of Nomad and Mesos. They're like, oh, I'm going to put containers onto the cloud, and those containers are going to get scheduled onto different machines. But scheduling a container is not really that much fundamentally different than scheduling a virtual machine. It's just at a different level of the abstraction. So why do we care? Why do we need to know this? I'm just going to deploy my app into the cloud and everything's going to be magical and unicorns and stuff like this. But this is a microservice conference. So I would imagine a lot of people here are using Docker. How many people are actually using Docker? More than half the audience, almost 3/4 of the audience, right? So we're all deploying containers onto the cloud, and there's a lot of ways to deploy containers, right? Like you can I talked to some people that have their own bash scripts that they deploy. We used to deploy with Ansible. But over time, we're doing microservices. Maybe now we have 30 or 40 microservices on our team. And maybe we have 20 or 30 instances of each microservice. And we're trying to deploy it at a scale, right? And that's where we need to find something like a distributed scheduler to help us offload the ops work. So my team, just to give you a little background, my team works on this database called Vulkan. And basically, Vulkan is a port of Prometheus. So Prometheus is actually by the SoundCloud guys, and it's a monitoring system. But basically, what we've done is we built a distributed version that can store many terabytes of metrics. And kind of my talk today is kind of be about how we actually deploy this distributed database into production and run it operationally. I'm not going to talk too much about the code or how it actually builds. I have plenty of talks online. If you Google my name, you can see talks about the actual coding portions of it. But today we're going to talk about how we actually deploy it and what are the operational aspects of running a distributed database. So just to give you some background of the requirements of this application, they're pretty tight. So they're not your typical app. So we have 3 gigabits of traffic exception a second. We have 20 terabytes of storage that we need while maintaining 100 millisecond read times and 100,000 writes a second. So this is like a very high performance application, and it actually very low latency. Basically what we're doing is we're storing metrics for all of our customers' virtual machines. So we have maybe 1 million virtual machines that we're taking CPU and memory and process metrics, and we're storing in a central database, and we're allowing the users to access this data. So originally, I don't want you to memorize this slide, but just so you have an idea. Originally, when we deployed this application, I started at DigitalOcean about 2 years ago. And the only primitive we had available to us was virtual machines. So what did we do? Every single thing was a virtual machine. So we ended up maybe with 100, 200 virtual machines to run our architecture. As you can see, we actually have quite a varied architecture. And I'm going to talk about our architecture so that way you can understand as we've moved pieces from virtual machines onto distributed schedulers, like what are the different pain points we found for each portion of the app. So you can see here in blue, we have a whole bunch of microservices. And the microservices are all stateless internally, right? They're just, we write them in Go. They're deployed as containers. They're very kind of standard for microservices, pretty much everybody's been talking about. But then we have a couple databases, right? We have a traditional MySQL database for keeping track of auth data. And we have a very massive Cassandra node. So our Cassandra cluster has about 20 terabytes of storage in it. So it's pretty well scaled out Cassandra instance. Also, we have a message bus in Kafka. And Kafka is keeping a couple hours of data inside of it. So we have multiple different places where we actually have state in the system. And the stateful pieces are the more interesting pieces as we start to move these into schedulers and stuff like that. So I want to step back and just go back to something very simple. This is an Arduino. Does anybody have an Arduino here? Yeah, about a quarter of the audience. If you don't have one, you should get one. They're really fun for hacking. But what I really love about an Arduino is that it runs a single process. You're like, what? How can a computer just run a single process? I need multitasking and all this? Nah, it just does one process. It does one thing. It's really amazing. And you don't think about it, right? And you're like, okay, well, that's cool. So what is the next scale up, right? What's the next level up is a Linux machine, right? Or a hypervisor. What is a Linux machine really giving you? It allows you to run a whole bunch of applications, right? It allows you to have virtual memory isolation. You can have process isolation. It gives you disk storage and networking and CPU, right? Like, there's a lot of things that now we have a scheduler running on a single physical machine, and it's kind of giving you this isolation. Well, what are the processes? The processes could be a virtual machine. Like if you go onto our hypervisors, you'll see 100 virtual machines or 10 virtual machines running as processes on the machine. Maybe if you're running Kubernetes on the metal, you'll see Docker images being running as processes, right? So now that we've made the leap, we've started off with a machine with a single process. Now we have a machine with multiple processes. What does it look like when the entire data center becomes one set of processes, right? And that's kind of what the idea behind a distributed scheduler is you're basically trying to take your entire data center, or at least a portion of your data center, and treat it like it's a single physical machine, but it's not, obviously. It's thousands or hundreds of physical machines, right? But there's other things that it does that a normal scheduler wouldn't do, right? It needs to know about containers, or it needs to know about virtual machines, right? And instead of giving you virtual memory, it has memory quotas or CPU quotas. You can only this process can only run with one CPU. Maybe it can only run with 2 gigs of RAM. And you're kind of defining these things to kind of carve out your different portions of your cluster. Maybe even the network traffic. Maybe your application only is allowed 1 megabit of network traffic, right? But that's what a distributed scheduler is doing. It's trying to allocate these resources across the network for you. So there's a really popular one called Mesos. And I think they actually have a dev team here in Berlin. And anybody here use Mesos by chance? There's 1 guy, 2 guys? Okay, cool. So one day we had a bunch of new network admins come to our company, and they built out a Mesos cluster. And we bought like about 10 racks of servers, 1,000 machines or something, and it was going to be magical. And they're like, okay, we're going to run all of our internal apps on Mesos. Okay, everybody deploy. So what we did is we said, cool, this is awesome. This is going to be great. Like all of our problems are gone. We won't have to do DevOps anymore. So what did we do? We deployed our entire application on Mesos. What happened? Well, we had a production outage. But we'll get to like why that happened. So Mesos is really cool because it gives you these really nice dashboards. So you see this, and you look and you're like, oh, my entire cluster is just a dashboard. It looks like a single computer. But now instead of a single computer with 30 cores, I have 1,000 cores, and I have a terabyte of RAM, right? And it kind of lures you into this sense with like these .uis that like, oh, things are really easy and this is going to be really wonderful. And how does it kind of work underneath? So I kind of touched on this a bit before, but traditionally, like when we deployed apps, right, we would have a web server. Then we would have a Memcached server. And then maybe we would have a Hadoop server, or we'd have a database server. But you would find was that your web server was using lots of CPU, but it wasn't using memory. So now you have all this wasted memory, right? And you're like, well, I'm going to resize my VM, or what you did is maybe you took your Memcache and you run your Memcache with your web instances. And then you're like manually like shuffling around processes to reuse resources between machines, and you're like, this is just a total waste of time. So instead, what Mesos tries to do is you define what resources your app uses. So for example, like something like a database or Hadoop would say, I need lots of I/O resources, but I don't necessarily need a lot of CPU resources, right? And then your web app would say, I need 4 CPU cores, but I only need 1 gig of RAM. And what it does is it tries to figure out, based on these constraints, how to place the instances on your cluster so that way it efficiently uses all of your hardware. So maybe before you were using 200 boxes, and now you're using 100 boxes of hardware. And one, from a cost perspective, yeah, sure, less hardware is cheaper. But then also just from a sysadmin point, right? If you're managing half as many boxes, you need half as much sysadmin time, right? So there's like a lot of really nice benefits that you want to see coming out of something like Mesos. And this is just another picture of kind of the same thing I was talking about, where different portions of the application will just kind of follow themselves onto different nodes. And you don't really care what physical machine it's running on. It just kind of handles that for you. Or so it seems. So we will talk about that. So cool. So we started to deploy our application on Mesos, which is really easy. They have they have another UI called Marathon. Okay, this is cool. So Marathon is another scheduler that runs on top of the Mesos scheduler, which runs on top of your Linux scheduler, right? So you're like, okay, I guess that's one more level of complexity, but fine. They have a nice UI, so all is good. What's really awesome is they have like this really nice JSON format. And you define your application as a JSON file. And it's like maybe 30 lines long. You say, I want 2 CPUs, I want 2 gigs of RAM, here are the configuration values, and here's the Docker image. And boom, and it does it, and it deploys it onto 100 machines, and you're like, boom, I'm done. This is awesome. So for like your microservices, this is really nice. This works really, really, really well. But we were like, we're going to run everything on top of Mesos, because that's the future. So first, we tried to take Kafka. So Kafka is kind of a persistent message bus. And for us, we maintain maybe a couple hours of temporal data in our Kafka bus. And when you deploy Kafka onto Mesos, it has a very funny thing. So it says, oh, you shouldn't just deploy Kafka as Kafka. We have another scheduler that runs on top of the Marathon scheduler that runs on top of the Mesos scheduler, which runs on top of your Linux scheduler. And you're like, okay, I guess. So you deploy this custom Kafka scheduler onto Marathon. And once again, it gives you a bunch of really cool interface. It gives you this command line where you can say, all right, I want to spin up an extra Kafka node. I want to put a new topic. I want to give an extra 2 gigs of RAM to every instance in my Kafka node. You can do all these amazing things. You can scale it up. So we had a terabyte instance of Kafka running in 10 minutes, right? And we were like, this is awesome. This is the best thing that has ever happened. Like, we're done. We don't have to ever do ops again. So if you know about Kafka, Kafka is pretty cool. So if you lose a node, you're okay. You lose a couple nodes, you're okay. You lose 3/4 of your nodes, you're probably going to start losing data. So we had a production incident where in one of our New York data centers, we had a network split. So like half the data center couldn't talk to the other half of the data center, which, as we know, doing network applications, this is a standard thing. Like, network partitions happen. They're guaranteed, right? So Mesos is really awesome in network partitions. It says, you know what? If I can't talk to the master, I'm just going to kill everything. You're like, that's probably not exactly what I wanted, but OK. So that means I lost half my Kafka instances. Even with 3x replication, I lost data. Thanks, Mesos. I really appreciate that. So Mesos has some really kind of very hard conditions on network failure. It does not handle network partitions very well, which is very strange considering it's supposed to be a network distributed operating system, right? So that was clearly not going to work well. So we took Kafka off of Mesos. The other service that we were trying to run on Mesos was Cassandra. And if you guys know, Cassandra is like a very high-performance database. In our case, we're trying to store maybe 20 terabytes, which isn't enormously large, but it's quite large. And we really had low latency requirements. So we didn't really want anything else to run on the nodes that ran on Cassandra. So what did we have to do to run it on Mesos? We couldn't use any of the orchestration. We had to say, Cassandra instance 1 runs on server A. Cassandra instance 2 runs on server B. Nothing else is allowed to run on server B. Nothing else is allowed to run on server A. So we ended up having to manually partition our servers that ran Cassandra. So you're kind of looking at it and you're like, why is this better than just running just virtual machines? It's not any better. You've now added an extra layer of orchestration with no advantages. Because the problem is when you have like a stateful service, that state exists on disk. So you have to come back to the same disks if you want that state. So the whole point of these distributed schedulers really gets killed when you start to do things like very stateful services like Cassandra. And I wanted to kind of touch on, Mesos is really complicated in a lot of ways. It's very powerful. So you can have all these different kinds of schedulers that spin up jobs. So they have like a custom scheduler, which is called Kronos, that can do things like cron. So you can have a network cron job, and the cron jobs can just run on any machine, and you don't have to set up cron. So it's like really cool that you can do things like this. But the level of extra complexity, we found that it was really not worth the pain that we got out of Mesos. So we pretty much got rid of Mesos completely from our architecture. Now, I've only said bad things about Mesos. I am going to come back and say some good things a little bit later, but like I have to like let the pain sit in for a minute because I was really upset with some of the failure conditions of Mesos. So we went to the far extreme. After we had this network partition, I was like, I'm going to find a scheduler that can handle any network partition under any condition. And if you want that, it's called Nomad. It's actually written by the Hashi Corp guys. So if you've ever used Console or if you've used Vagrant or some of these things, they also have their own distributed thing. You probably haven't heard of it because nobody uses it. But it is really awesome. So what's really cool is the Hashi Corp guys, they have their own gossip protocol. And their gossip protocol allows servers to communicate with each other in the same data center and between data centers. So you can have network partitions, and the servers that can still talk to each other can still be updating state between each other. And when the servers all become back together, they can become eventually consistent with the state in other data centers. So you can potentially have a data center go offline for an hour, or a network partition between two data centers go off for an hour or two, and you can still have your app running in both data centers. So it's really awesome. We looked at this, and it was really cool. The reason we didn't go with Nomad is basically we couldn't find anybody else that was actually running a production application using it. And they kind of gave up on stateful storage. They pretty much said, we're not going to handle stateful storage. We're not going to handle databases. That's too hard of a problem. We're just going to punt. So we were like, maybe it's just not worth it for us to really go into it. So we ended up siding on Kubernetes. I bet a lot of people here use it. How many people here are actually using Kubernetes? Okay, only like 5 or 6 people. Cool. Actually, that's better. I thought maybe a whole bunch. So Kubernetes, once again, I was like, oh no, I'm not going to get tricked again with these fancy dashboards and all this. I was like, that's not cool. You can't fool me again. But Kubernetes has been really amazing. What's really funny, I think why I like Kubernetes is I don't ever look at the dashboard. I have never once. I don't even know where the dashboard is for our Kubernetes install, actually. Because we've actually done a bunch of things to like hide some of the complexity of Kubernetes. So there was actually a couple talks earlier. Actually, I'll get into that in a second. But the architecture of Kubernetes is like a lot simpler than Mesos. And it was clear because it was written by the Google guys that had worked on Borg. So they had already built a system like this before. It's very hard actually to see in this diagram probably, but basically you have an instance called a kubelet that runs on each one of your physical nodes. And the kubelet is basically talking back to a master Kubernetes instance that actually keeps the actual scheduler. So if there's a disconnect between your kubelet and the scheduler, your applications still run. It doesn't have the same kind of failure conditions. And it's really a lot simpler than Mesos. You don't have schedulers on top of schedulers on top of schedulers. And we've had a lot less failure conditions actually happen with our Kubernetes cluster. So there's actually been a couple talks today. Like I noticed that the Weaverworks guys had a talk yesterday about how they have their own custom language for Kubernetes. We have our own custom internal language for Kubernetes also. So the Kubernetes YAML file is actually quite verbose and annoying. So what we did is internally we have a JSON format, and we just have a program that converts our JSON into the real Kubernetes format, and it really simplifies it a lot. So that way we can just write like 30 lines of code here, and this is the entire deployment for my production system. So, I mean, if you use the core Kubernetes, maybe you write 100 lines of code instead of 30. But that's something that was really cool. We should probably open source this, actually. And the other thing we do is we only deploy from the command line. We have our own little tool that does like command line deployments and pushes to Kubernetes. I don't use the UI anymore. I think the UI is always kind of fools you in different ways. So this has been a good thing. And the other really kind of cool thing that we're doing is diffs. So there was another guy, I can't remember which talk, but he was talking about a tool called kubediff. So whenever you do a deployment into production, you diff what is in production versus what you think you're going to deploy. Because what has happened a couple times was somebody pushed something into production, and they didn't save the configuration into Git. And I went to go deploy to production, and like I would maybe change what he had changed, so we would overwrite each other's work, right? But as soon as we added diffs, and you have to verify the diff before you're allowed to deploy, you make sure that you never make mistakes of like just overwriting other people's work. Even on a 4-person team, it's very easy to have multiple people doing production deploys, right? So this is something I really recommend. Like even if you're not using Kubernetes to do this diff-style deployment, is something that was really helpful. All right, so that was kind of a mouthful. And I wanted to take a step and talk about what our final architecture ended up looking like. So after all the pain, really the only things that moved into Kubernetes were microservices. And things like Cassandra, actually we moved them off of virtual machines onto physical hardware because the performance difference was actually quite a bit for us for that use case. But we found that Kafka and MySQL and Cassandra, there's not a good solution right now. I think in the next year or two, maybe Kubernetes will get there, but I don't believe there's a great solution to running stateful services on Kubernetes or Mesos at the moment. You can, but I think that the benefits like outweigh the advantages. The other kind of issue that we ran into with Kubernetes, which maybe a lot of people won't have this problem, but we have 3 gigabits of network traffic a second that's coming into the application. And we actually have multiple physical 24-core servers that just handle load balancing. And one of the issues with Kubernetes is it tries to like, you have a load balancer run per cluster, but the load balancer is just like a portion of one machine. It's It's just a container running on a portion of a machine. But we needed like multiple physical machines to do Kubernetes, to do load balancing. And there was no real easy way to scale up the load balancers properly with Kubernetes and Flannel. So really high bandwidth, high throughput applications, we weren't able to get onto Kubernetes. But that was luckily only one small portion of the system that we weren't able to move on to Kubernetes for that reason. So metrics and monitoring. I always like to talk about metrics because I'm on a metrics team. I build a metrics product, so I'm interested in doing metrics of my own system. And I think I'm a big fan of Prometheus. The Prometheus guys are here in Berlin. It's an awesome project. InfluxDB is also really cool, but whatever you like. I wanted to show how we actually deploy our metrics, how we do metrics on top of Kubernetes. So the typical pattern you'll see most people do with Kubernetes is you'll actually spin up an actual Prometheus Docker image inside of your Kubernetes cluster. And that Prometheus instance will scrape all the Docker instances that run in the Kubernetes cluster. And then if you still have physical machines, like we have virtual machines or physical machines, you have to run a separate Prometheus instance that runs outside of your Kubernetes that's collecting all of those. And then what we do is we just use Grafana as kind of the way to like join all the metrics together into one UI. So that way, like, it's not so obvious that our services are running in different places, but it allows us still to have one dashboard for our entire system. The other thing, the next core portion is logging. When you move on to like Mesos or Kubernetes, you totally lose the ability to do disk-based logging. So like a lot of apps will just write to a file and then rotate that file, but you can't do that when you're in a container, right? Like, so kind of the approach that we've taken is we use syslog. So so every kind of Kubernetes node has syslog configured on it. And what we do is we allow the Docker containers to allow them to write into the local syslog on the local node. And those syslogs forward to an rsyslog aggregator per data center. So like in New York, we'll have an rsyslog aggregator. In London and Frankfurt, we have different aggregators. And then those aggregators eventually will write into Elasticsearch. And now we have something like a 20 terabyte Elasticsearch cluster of just logs. And we just use Kibana to do the visualization. And I said I wanted to mention that I was going to say something nice about Mesos. So the team that runs our logging cluster uses Mesos, and they're running like 200 servers to run our logging cluster, and they're running it all on Mesos, and it's actually running well. However, they have to manually configure all 200 servers to be certain partitions of the Elasticsearch cluster. So there was a total manual setup of the Mesos. So they didn't get to use any of the nice scheduling features to actually scale out their Elasticsearch cluster. But it does run on Mesos, and they do get, I guess, some small advantages. I don't personally think that they are worth it, but yeah, so just kind of to recap, I really think the big advantages are DevOps. Like, I was spending 50% of my time doing DevOps work, and for me, I'm a developer. I'd rather be coding. And being able to just take my containers and throw them on and scale them, I think that was a huge, huge win. I think anything you have stateless, I would just throw it on Kubernetes today. But you have to look at your abstraction. So like everybody's going to talk and say, oh, Kubernetes or Mesos is so awesome. We should all move it. But there's a lot of extra work that you're doing. And I don't believe that in a lot of cases you're getting much benefit for that work yet. I'm hoping that over time they're going to kind of improve these things, but at the moment I don't really believe that they work well for databases. I don't believe that anybody has solved this. Maybe internally at Google they have something, but nothing on the open source have I seen that actually does that kind of abstraction. So that's kind of where I want to leave it. I understand this is some kind of German expression. And that's the end of my talk there.
Thanks a lot. Any questions? Sorry.
Great talk, Matthew. Thank you very much. I was curious, was it a slight fair comparison between Mesos and Kubernetes? Because Mesos, when you were mentioning you're running stateful workloads, and then Kubernetes not stateful. I was curious, in your opinion, say you'd only gone with the stateless stuff on Mesos, do you think it would have been your thing or not?
Yeah, that's a great question. Because we were trying to do much more ambitious plans on Mesos than we did on Kubernetes. I think a totally stateless operation on Mesos probably would have worked okay. However, the failure conditions, because my idea is if the Mesos or the thing fails, my app should just keep running. And I just shouldn't be able to deploy new versions of the app maybe. But that condition that it kills stuff was really just kind of a deal breaker, at least for me.
Okay, more questions?
Which of these schedulers are rack aware?
So, that's a great question. Which ones are rack aware? So I believe they're all rack aware. Well, at least Kubernetes and Mesos are both rack aware. Because for the obvious reason, you have this with Cassandra too. If you have a physical rack get destroyed, you don't want to have all of your instances happen to be on the same rack, right? I don't think Nomad did. But the only other thing about being rack aware is you also have to make sure that like your cloud provider supports rack awareness. Or if you're running your own data center, sometimes you don't know where your physical nodes are in the data center, so you can't actually set up the rack awareness properly. But that's definitely something you really need to be aware of.
Okay, more questions? I don't see any. So, thanks a lot. Thanks a lot for the talk. Thanks a lot for being here.